There are three political parties or players, A, B, and C. They're located in a parliament, and each political party has some seats. So A has 45 seats, B has 45 seats or vote, and C has 10. All right, so the total 100. Well, the thing is, they're going to be voting on some proposal, and according to this proposal, they're going to split $100 million. Doesn't matter, to be honest. They're going to just split some surplus among themselves. So in that example, it is 100x, I mean, who cares? Some surplus as well. You may confuse it with our notation with set. Some surplus, say it is 100 million. Well, the thing is, for the proposal to pass, they need the majority of the votes. So 51 or more votes is required so that the proposal is going to pass. All right, so that's it. Well, if the proposal passes, obviously, well, that, I mean, what is included in this proposal? For example, if political party B and C forms a coalition and approves the proposal, well, obviously, this proposal is going to say how they are going to split the $100 million between political party B and C. Well, obviously, they can give something to political party A as well, but they don't really need to. Because any proposal can be approved as long as B and C forms a coalition, all right? So that means basically they're going to split $100 million between, between B and C. However, if A and B forms a coalition, well, then that means they're going to split any way they like $100 million between themselves. Again, they can give some money to political party C, but again, there's no point of doing this. Because they already formed the winning coalition, and hence any proposal will pass even though party C gets nothing. Okay? Well, again, as I said in my lecture videos and the lecture notes, I have another example where we have 4 political parties. So that one is, relatively simpler. You'll see, because when we work on nucleus, kernel, calculations are going to be much easier when we have 3 players. All right, well, what would be the worth function in this problem? Well, kind of simple, because we need the majority and no party has the majority. V of A, V of B, and V of C, meaning when they do not form any coalition, every party behaves, sort of a single, well, then it's going to be 0. You may kind of wonder, is like, this is going to be a voting, right? They're going to vote. So they're going to vote either approve the proposal or not approve the proposal. So it's kind of there are 2 things you can vote, accept or reject. So, well, again, it's like, if no coalition is formed, that means they cannot also create the proposals, like how to distribute. And so whatever the proposal comes, if there's no sort of majority winning coalition, everybody is going to be probably unhappy with the proposal. And so everybody is going to reject. So think it that way. For that reason, VA, VB, VC are all equal to 0. All right? What else? Well, the winning coalition can be formed. I'm going to ignore the brackets. So I'm going to just write V of AB instead of writing V of A comma B. Okay, so you understand what I mean by this. So V of AB and V of AC, or, V of BC, they all actually form a winning coalition in this game, right? They are all, well, and also, by the way, V of ABC. They are all equal to 1. Because as I said, it's like A and B has total of 90 votes. And by the way, we assume, without loss of generality, that all the members in each party is going to vote exactly the same thing. So for that reason, when we say coalition A and B will be formed, that means all the members of A and B are going to vote yes. All right. By the way, that's usually what happens. So A and C also forms a coalition because the total is 55. B and C as well, and the grand coalition as well. So this is, by the way, super additive game. So therefore, we can just assume without loss of generality that at the end, the grand coalition is going to be formed, ABC, although we don't need the grand coalition. Any coalition of two party actually is fine, but we can assume without loss of generality that the grand coalition is going to be formed. So therefore, we talk about payoff vectors, something like XA, XB, XC. So some of them can be 0. And remember, the feasibility implies, each of those, XI, let's call it, is non-negative, all right? And V of, XI is how much surplus they're going to get. And XA plus XB, the feasibility requires that this summation has to be equal to 1. Well, why it is summing up to 1? Remember, we said they're going to split surplus 100. Who cares? It's just the proportion. What is going to be the ratio of surplus party A will get, party B will get, party C. So XA, XB, XC is basically the share of surplus. All right? So for that reason, when I add them up, I add it up to 1. But if you like, you can add it up to 100 million. But I don't really want to deal with, zeros, 100, whatever. It's just, the share of the surplus. That's all I care. Then later, you can just multiply it by 100 for each player and then get the exact amount if you want to. But you don't really have to. So that's basically what feasible payoff vector will be. So the first question is, what is the stable payoff vector or solution in this problem? Or what is the core? All right, so any idea?
Would it be 1/3 for every party?
Good guess, right? I mean, you can definitely make a guess. So let's consider this 1/3, 1/3, 1/3. Is it in the core? Good start. What do you say?
Well, it's in the core, right?
Is it? How can I check if it is in the core or not? Does any coalition have incentive to deviate and form a sub-coalition? Right? That's the idea of, sort of intuitive idea of core. Well, here, think of party A and B. All right? Actually, you can think of any two party, but let's look at A and B. So what do they get at the end? 1/3 plus 1/3, 2/3. This is totally what they get. However, if they ignore political party C and form their own coalition, right, A and B only, and basically ignore party C and give him 0, well, what's going to happen? This proposal will pass because they certainly pass the majority. So therefore, they can split the entire one among themselves. For example, they can say, hey, instead of sort of agreeing to this proposal, why don't we get together and share it half and half and give player 3 nothing? What's going to happen? Well, clearly political party C is going to reject this proposal, but who cares? Political party A and B will certainly accept this proposal. Why? Well, because both political party A and B gets higher surplus. So therefore, the X is not a stable solution, stable outcome, or stable payoff vector. Because players, or the political party A and B in this instance, has a sort of incentive to deviate to this one. But it's not only A and B, by the way, A and C or B and C. So any two party actually form a smaller coalition, all right? And can make them, both of them, better off. By the way, the stability is somewhat related to Pareto-optimality, right? I mean, I don't know if you can see the relation, kind of. I mean, kind of, not exactly the same thing, because Pareto-optimality cares all three players' well-being all at the same time. But here, it's just, two players' well-being is what's considered in core, all right? So it's like, can two players get better off? Or can one player, well, one person deviation is not optimal, obviously. I mean, if political party A says, I'm going to leave you guys and bring my own proposal and vote yes. Well, unfortunately, nothing is going to be profitable for political party A because he doesn't have the winning coalition. I mean, he doesn't have the winning vote. He has only 45. He needs another party to approve his proposal. Obviously, political party A can propose something like this: 0, 1/2, 1/2. Instead of this, if political party A leaves and offers this, obviously political party B and C will prefer this one over this one. All right? But nevertheless, going from this to this is not a profitable deviation. So these are deviations. Remember, in non-cooperative game theory, we have deviations from one strategy to another strategy. So here, the deviations are kind of from one payoff vector to another payoff vector. Can you find another payoff vector where the deviating coalition is going to get better off? Every member of the deviating coalition will get better off. All right? So I hope that is clear, that 1/3, 1/3, 1/3 is not stable. Is that clear? Any question? Good.
It's clear, but then would it, for the 0, 1/2, and 1/2, that's also not stable, correct? Because then the person that's getting 0 can say that you can have more than 1/2, and I'll take, let's say, 1/3, and you can take 2/3.
Exactly.
We can leave the other person out.
Exactly. So this is this stable? It's like we would like to deviate 1/3, 1/3, 1/3 to 0, 1/2, 1/2 maybe. But the thing is this going to be stable? I mean, by the way, it doesn't matter who has the 0. Let's say this is 1/2, 1/2, 0, because player A and B wanted to deviate to this one, remember? Well, is this stable? No, this is not stable. Why is that? Well, because this time, political party C will probably approach to one of those political parties, say, for example, to A, and political party C is going to say the following: look, I know you're getting 1/2, but I'm offering you 0.6 rather than 0.5, and I'm going to get the rest. Okay? Would you accept this one rather than this? Political party A is going to say, sure, because I'm getting more surplus. Political party B is going to say, no, but who cares? A and C jointly have power to pass this proposal, and obviously political party C is getting better off. So that means there is another payoff vector where some coalition, all the members of some coalition can get better off. And so therefore, this payoff vector X is also not stable. So, good. Well, we can keep guessing and then verifying. But the thing is, if the core is empty, well, I mean, there's no way, right? I mean, you can't find a payoff vector and show that. I mean, you can't go over all payoff vectors and show all of them are not stable. I mean, this is impossible because there are infinitely many payoff vectors. And for this problem, core is empty. So we need to prove it formally. Because as I said, there are infinitely many vectors and we cannot go over each one of them. So how do we prove it? Well, kind of simple. Because remember, by the way, for notational simplicity, instead of saying xi, I'm going to say the following notation, okay? So A, B, C. So let's get rid of notation, x1, xa, xb, whatever. So A is basically what political party A is going to get, B is what B is going to get, and C is what political party C is going to get. Okay, obviously all of them are positive, and on top of that, AB plus C is equal to 1. This is the feasibility condition. Good. Well, so what is the stability? Now I need to sort of understand the formal definition of stability. So if you remember, the stability basically says the following. For any S subset of N, obviously non-empty, right? For any S non-empty. So let me copy the notation here because I don't want to change the notation. Let me keep the notation same. So core is basically the following. X in R to the power 3, okay, such that summation of X, which in this case, summation of Xi, all right, let's denote this notation. I is in some sets S. Well, in the lecture notes, I used C, I'm sorry. Here I'm going to use S, greater than or equal to V of S. And that is true for all S subset of N, the non-empty obviously. Okay, so that's the formal definition of core in this specific problem. I mean, here it is R3 because we have 3 players, and the rest is the same. So what does that mean? That means you first need to sort of figure out what are those possible subsets, right? Well, I mean, S is coming from this. So, well, it could be A only, it could be B only, C only. Well, obviously I have those brackets, but I really don't want to use the brackets because it's very time consuming. So AB, again, it's like I'm abusing the notation slightly, but you understand what I mean. This is a set, all right? AC, BC, and then finally ABC, all right? So these are all coalitions that I am actually considering here. There's no other coalition in this problem. Okay, well, what else? Well, this is going to generate, lots of inequalities. So I need to write all those inequalities. So what are they? Well, remember XA, I'm going to use the notation A because, again, trust me, it's going to make my life easier later. So this one, for example, when S is equal to A, basically means the following. A is greater than or equal to V of A. So what is V of A? Remember, V of A or B or C is all 0. So 0. So that means A is greater than or equal to 0, B is greater than or equal to 0, C is greater than or equal to 0. So basically these inequalities doesn't really tell much to me. I already know that from the feasibility of the payoff vector. Okay, let's keep going with the coalitions of 2 members, AB for example. So what is summation xi when S is equal to AB? Well, it means xa plus xb, right? I mean A plus B, greater than or equal to V of this coalition. What is it? Remember, as long as there are 2 or 3 members in the coalition, V is always equal to 1. So A plus B is greater than or equal to 1. What else? A plus C is greater than or equal to 1 because of coalition AC. And then B plus C greater than or equal to 1 because of this. And then finally, A plus B plus C greater than or equal to 1. All right. So the question is there any ABC vector in R3 which satisfies all these 3 properties? Plus, don't forget the efficiency, obviously, right? Because I can give A and B and C very large numbers like 1 million, 2 million, whatever, 10, for example. Obviously, A is 10, B is 10, C is 10 is going to satisfy all those inequalities, but again, it is not feasible. So be careful about that. Okay, so I have a system of linear inequalities and one equality, so I need to solve that. But I think that is kind of straightforward, at least for this problem. So this has to be 1. How so? Well, I mean, look at this one. A plus B must be greater than or equal to 1. But you know A plus B plus C cannot exceed 1. So therefore, I can fairly say A plus B is equal to 1, right? I mean, it can't be greater than 1, to be honest. Because C or B or A, they can never be negative. So A plus B has to be 1. But what does that tell me? That tells me that C is equal to 0. Well, okay. Let's go with this one. B plus C greater than or equal to 1. But I know that it can't be greater than 1 because they have to sum up to 1 at most. So that means B plus C is in fact equal to 1. But what does that mean? That means A must be 0. Okay, use this one, A plus C greater than or equal to 1. It actually means exactly equal to 1. A and C, if it adds up to 1, well then that means B must be 0. Well, if all of them are 0, how come I have A plus B plus C equals 1? Well, okay, that's impossible. So what does that mean? That means, it doesn't mean that you are confused. No, it means the system of inequalities confused. It's a contradiction. So what does that mean? That means there is no ABC which is going to satisfy all those, I don't know how many, 1, 2, 3, 3, 6, 7, 7 inequalities. Okay? So hence, because of this contradiction, core is empty. So you don't really need to make a guess and then show that there's going to be a deviation. It's just, one sort of simple proof shows you that the core is empty. Or maybe if core is not empty, if it was not empty, well then I would actually capture the values of A, B, and C's that is going to satisfy those inequalities. I mean, I could characterize or find the core payoff vectors by doing this approach. Okay?